Check. Ah. Okay. I'm proud to announce you Markus Nutzing and sorry. I'm proud to announce you Markus Nutzing and yes, and Rainer Peusel. I'm sorry, it's a bit late. Yes, they talk about steganography in auditive signals, so embedding hidden information into other audio communication. And I think this is a very interesting topic, and now give them a warm applause.
Test. Geht's? Okay. So hi everybody, thanks for coming. It's pretty late already and joining our lecture about configuring monitors for presentations. Now it's about steganography in auditive media, and we generally present the results of our research project at our University of Applied Sciences in Austria. And this presentation has been created by three guys, two of them being here. This is Markus Nutzinger and me, Rainer Peusel. Before we start the talk, I wanted to let you show hands of how many of you know the difference between steganography and cryptography. Okay, that's quite a lot. We also included some slides about what steganography is compared to cryptography. I want to let you show hands once more. So how many of you use tools for steganography consciously in the daily life? That's not too many, but I think it's 2 or 3 people. Okay, so let's get started on the topic. So cryptography, as almost all of you might know, is the study and practice of hiding information. So we want to protect secret information, and the most important thing and the biggest difference between cryptography and steganography is that the data transfer is obvious. So in steganography, we want to communicate over covered channels, and we want to conceal the existence of secret information at all. In this context, I also want to mention cryptology, and cryptology, it's almost the same as cryptography. The difference is that cryptology also includes cryptanalysis, meaning to find out if a cryptographic approach has been secure. I also want to give a brief introduction on how steganography works. So we have a cover medium. In this example, it's an image. And in this image, we embed secret information. Here it's called secret message, using a so-called encoder. And this encoder gives you a so-called steg object. So it's the cover medium modified somehow a little bit, and it represents the secret information then as well. Then this steg object is transferred over the communications channel to the receiver, and the receiver can also be understood as the decoder, and the decoder is used to get the secret information back out of the steg object. Some of these decoding algorithms need the original cover as well, so that's why there is a dashed line here. And we also have a key which can be used to determine the places where the secret information, for example, is hidden, or as well the data can be encrypted before its transmission over the secret channel. To give you an example of where this methodology can be used, I included a map of the world. It's from the OpenNet initiative, and it shows countries in which there is some internet filtering going on. And often in this country, it's used to communicate over unencrypted channels, for example, GSM networks or voice over IP channels as well. And this is lots of these countries can be understood as those in which it can make use to use steganography as well. Let's talk about the framework, as we call it, to identify the major components. So this is one side of the communication, meaning it can be either the receiver or the transmitter, and we provide full duplex communications. So here we have the so-called framework. It's colored, and it includes embedding as well as extraction algorithms to modify the cover medium to create Steg object on the one hand, and on the other hand it allows to extract the secret information which has been embedded into the cover medium. And we also have a GUI, a graphical user interface, which allows us to control the whole process of extraction and embedding, and we can also supply the secret information in kind of a chat. We'll show you this later when we do the live demonstration setup. Here we have a picture, an image, which shows the setup for voice over IP. And in voice over IP we have two computers, one on the left, one on the right. Both have a voice over IP client installed. And they both communicate over the internet. And to do so, they both connect to a router. And we described here that it's a Linux router. And this Linux router we extended by some software, which I show you here, to modify the packets in real time. So, on both sides of the communications, we have extraction and embedding going on. This is a requirement as we want to communicate full duplex, so that both sides can send information. Sorry. One other important thing is that we have here the so-called net filter queue. Does anyone of you know the net filter queue in Linux? Heard of it? Just show hands. Okay, that's a lot. I would say it's 30 of you. The net filter queue allows you to manipulate network packets in user space. So you don't need to program a kernel driver, because usually, and at least in Linux, the TCP/IP stack is implemented on a kernel level. And so you're able to modify packets in user space. So let's compare this setup to a setup for GSM communications. And the setup is pretty similar. So we have on both sides, like receiver, transmitter, and the framework, which is on both sides used to embed information into the cover medium and to extract it as well. But instead of using routers to communicate with each other, we use mobile phones, which communicate over the GSM network, which is here displayed as just a line for simplicity. Another important thing is that on the routers, we use the net filter queue to modify the packets. Here we're using the sound card, the computer sound card, and on this sound card, we plug in a hands-free set. A hands-free set of the mobile phone, so we are able to modify the auditive information before it's handed over to the mobile phone, and we can also take the auditive information we get from the sender and to extract the secret data. So, as I've been mentioning the framework a couple of times, I think it's time to introduce you to the architecture especially. So first of all, one of the most important steps is just to identify the tasks involved in this secret kind of information exchange. So, as mentioned before, there is the embedding going on, so we need to unify the cover medium with the secret information. And before we unify these two data streams, we need to adapt or to extend the secret information with some protocol information. So almost all of you, I think, know that in a stateful protocol like TCP/IP, there is this integrity checks going on, segmentation of data, acknowledgement, secret numbers, just to be sure that the data arrives in the correct order. So we also need components for this job. And as well, we need, as in almost any software architecture, we need components for the instantiation management as well as interfaces to third-party software. So now that we have identified these components, we try to arrange them in kind of a layered model as we know it from the TCP/IP model. And to tell you how the communications work, we start at the topmost layer, let's say at Alice, and Alice wants to transmit the secret information to Bob. So the secret information is available on layer number 6 in kind of bytes. And these bytes are handed over to, the secret bytes are handed over to the so-called protocol layer, and this protocol layer adds some information which is required for the data to arrive in the correct order. And it also represents the data in kind of bits afterwards. And these bits are then handed over to the presentation layer, which is required in some embedding algorithms. So, for example, spread spectrum, we are talking about this later on, requires the data to be represented as chip sequences. And these chip sequences are then handed over to the actual embedding process, for example, this spread spectrum. And this embedding process takes these chips and puts them into the samples, which we get from either the routing process or from the sound card. Then, after that, we have these frames, and we need to make sure that both sides of the communications start decoding at the right time. So we need some synchronization. And after that, we take all the samples and put them on the bus, meaning handing them over to the routing process or back to the sound card after modifying them. After the transmission, when we've transmitted the data from Alex to Bob, the Stego object goes through all the layers in reverse order, as we did it when we sent them over. Here is a brief overview of the software architecture, and mainly the framework can be understood as an infinite loop. And in this infinite loop, we take audio information from the audio inputs, hand them over to the embedding or extraction process, depending on either if we're receiving data or if we transmit it to the other side. And after embedding or extraction, we hand it back to the audio outputs to continue the transmission of data. So, let's talk about embedding algorithms.
Okay, thanks. As we heard about the framework, one important part, of course, is the embedding and extraction. And for this, we need some algorithms. So first, we want to distinguish between two parts, the digital and the analog ones. Of course, everything is digital here, but we see the digital algorithms as those who process all the bytes or samples independently. So every sample, so like in the LSP hiding algorithm, the last bit of every sample, for example, is changed according to the secret data, but there is no, the adjacent samples are not looked at as an audio signal. On the other hand, we have those analog algorithms which take some samples, for example, say 100 samples, which correspond to some time, some milliseconds, and as we have this kind of signal, we can process it like we can do a Fourier transformation or do some signal processing operations with it. So in the following, we want to look at those three algorithms: echo hiding, spread spectrum, and phase coding. Oh yeah, first I want to make clear how do we get from the samples to this analog representation. So we have the ability in our framework to convert from some encoded audio data to the raw audio data. In our prototype, for example, we work mostly with PCM files, and we have these samples, and we do interpolation, so to get maximum precision, so increasing the sampling rate. And depending on the algorithm, so this is why we don't use LSP, because it won't work in this setup. It doesn't matter that we first interpolate, do our manipulations, and then downsample again. The algorithms still work. Okay, so echo hiding, I think it's pretty obvious how it embeds data. So it has three important parameters. There's the delay. So you define two delays, one if you want to embed a 0-bit and one if you want to embed a 1-bit. And of course, they need some spacing between them, because otherwise the receiver cannot distinguish between those two. Typical values for such delta, we used about 1 millisecond, and the delay shouldn't be too big, of course, because otherwise a listener would clearly hear some echo. And we chose the delay to be less than 2.5 milliseconds. Yeah, and the third parameter is the decay. So of course the echo can't be as loud as the original signal. It kind of depends on the signal how you would choose the actual delay. So we built in some kind of regulation. So depending on the last few milliseconds, on the amplitude of the last few milliseconds of the signal, we choose an appropriate delay. Okay, and another thing which is mentioned here is the block size. So of course you can't take one sample from the audio signal and introduce an echo. So you choose, for example, 20 milliseconds and introduce an echo every 20 milliseconds, and so the block size gives you the data rate more or less. Okay, yeah, generation, I guess it's clear how to add an echo. How do we detect it? There's a nice mathematical thing called Cepstrum. So it's, everyone knows the frequency spectrum, and the Cepstrum is just another transform domain. You need the Fourier transformation for it, you need the logarithm for it, and due to these, you separate the harmonic parts of a signal, echoes are harmonic parts, from the signal, and the idea is that the echoes are shown as peaks in the Cepstrum, so we can analyze them. Let's switch to an example. So here we have 160 samples. It's with 8 kilohertz. These are 20 milliseconds, some signal with an echo. Yeah, you have to believe us that the echo was really built in at with a delay of 1.25 milliseconds. And yeah, the Cepstrum shows the peak at sample number 10. If you do the math, it's 1.25 milliseconds. Yeah, you should note that this not always works that reliable. Think of silent parts, think of natural echoes, which may be in the signal already and disturb the receiver. Yeah, so it's kind of tricky for the receiver sometimes to extract all the secret data. Okay, next thing is spread spectrum. I think most of you have heard at least the term. So it's used in, for example, in UMTS with the CDMA mechanism. So the idea is to spread a narrowband signal over a large bandwidth. In our example, or in our case, we have bits, our signals, and we spread them over a larger, or that they need more time to transmit, more or less. So 1 bit isn't 1 bit, but gets transmitted as 400 chips, for example. And you are slower, but you are more robust. And to do this, you need some kind of spreading code. And this spreading code can be generated, for example, through a shift register. We do it that way, but you, of course, can also configure it manually or something. And of course, sender and receiver need the same spreading codes. Okay, now to the implementation. To get the data onto the audio signal, we first modulate our chips. So this is the already spreaded data signal, and we modulate it onto a sine carrier. And this modulated signal is afterwards added to the audio signal. But what is interesting here is that we, or if you do it like one step after the other, you would always have to calculate the sine, and we used another approach. We calculated one sine period, one template, with very, very much sampling points, so a few thousand, and we know how long a chip, how long is the duration of one chip, so the time, and of course we know the sampling rate. So for every sample we get, we know at what time it is if you compare it to a continuous signal, and so we know what point, so where in the period of one sine we exactly are, and so we just take the according sample and multiply it with our chip sequence to modulate our data onto the sine, and that way we also can do this sample by sample and don't need to buffer anything before starting the process. Okay, here's an example. So hopefully you don't see very much here because that's the chip sequence and it should be with very low amplitude. But what you may see is that the amplitude varies. So that's another thing we built in based on the average amplitude of the previous chip time. So for every chip, the amplitude stays constant, but we measure it, the amplitude of the audio signal, and depending on the last, on the average amplitude of the last chip time, we set the current amplitude for the next chip time. So yeah, that is why it varies, and this the above signal is added to the audio signal. And this actually does the embedding, and here we see the result. Okay, yeah, and this. So this is transmitted more or less, and the receiver gets the signal, and of course he wants to extract the data. So first thing to do, multiply with the sine, so with the carrier, and due to the phase shifts which were introduced because of the modulation, you get a signal which is sometimes, so for one chip time it's more in the positive values, for next chip time it's more in the negative values, and so on. And those average values over chip time are the input for a correlator, and the correlator matches the values which you get, like true, false, 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 true, 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 and so on, against the chip sequences which were generated at the beginning. So there's a specific sequence for a 0-bit and for 1-bit. And the output looks hopefully like this. So the blue line is the sequence which matched. So we had 100 chips for 1 bit, and yeah, like say 47 matched, or 45, don't know, which is still more than enough for the system to say, okay, I know this is a 0-bit or a 1-bit. And yeah, and the red line just stays about 0. So when I talk about correlation, you may ask, okay, but what if I miss the first chip? Of course, then the whole system is broken. You won't get any output. So big issue in this whole thing is synchronization. The receiver has to start at the correct chip, and which equals at the start of a bit. And yeah, so we have to search for this offset. And we do this. Okay, maybe I should first tell something about the implementation. So when receiving, we don't. The embedding is done in real time, and when we receive samples, we put them in an extra thread puts them in a buffer, and the main thread just processes further, so outputs the signal over loudspeaker or something. And in the other thread is just for extraction, so it fills up the buffer until enough time is there, and the embedding engine is notified, and then it starts this search process. So it assumes that the first sample in the buffer, so the beginning of the buffer, equals to the beginning of a bit. Of course, this may be true or not, but either way, the correlation from the previous slide is done, and you get some output. So it says, okay, with the probability of 0.2, this is a 0-bit or something. And we do this for, yeah, and we have some configurable granularity where we say, okay, and we try the next offset as at this and this time, and from inside the buffer, and so on. And we do this for the whole buffer, and the output is something like that. So we get a histogram which shows the bit qualities over time, and then so this, and then we have this dotted line which starts at 0, or I guess it starts a little above 0. But the point is, we increase it until there's only 2 peaks above the line. If this case is never matched, then we can't get synchronized anyway. That's how we programmed it. And we throw away the buffer, wait again, and start again the search. But if it happens to be the case, then we look at those 2 peaks, and for example here, one is at 0.19 and one is at 0.47 seconds. And if the distance, the duration between those 2 peaks is exactly 1 bit time, so the time it takes to transmit 1 bit, which we can calculate, of course, due to all the parameters, then we know we're synchronized. And then our new offset is like this distance, and we can start extract the further bits. Okay, yeah, the algorithms we've looked at so far worked in the time domain. So, as I said, there is no embedding delay. We can process the samples sample by sample. Yeah, but we also have the possibility to use another transform domain, in this case the frequency domain. Yeah, and for this we need the Fourier transformation, and as a fact we can't do a Fourier transformation from a single sample, so we get some embedding delay in this case. For example, we use 10 milliseconds, 10 millisecond blocks, so we get a delay of 10 milliseconds. Yeah, and as everyone knows, when we transform to the frequency domain, we get two spectrums. It's the frequency spectrum shown here and also a phase spectrum. And we can embed in either one. And yeah, there's another interesting thing which we implemented. In the time domain, we always modified the whole signal. So for example, the spread spectrum sequence is added over the whole audio signal. Every sample is modified in some way. But in the frequency domain, we can choose a frequency interval, and only those frequencies are affected by our embedding. So for example here, from 400 Hz to 1.2 kilohertz. Of course, the negative spectrum is modified as well. Yeah, and so we can, for example, adapt the specific algorithm to a specific channel or whatever. Okay, so how does this work? In our case, we don't use the frequency spectrum, but the phase spectrum. But anyway, the gray part is our affected frequencies, and this is split into two parts. And what is done is we calculate the average value of the phase values from each part, and the data is embedded, so one bit is embedded by the phase difference of the parts, and further if the difference is, so by the sign, more or less, by the sign of the phase difference. So we need to ensure at least a specific difference, and the sign tells whether it's a 0 or a 1. Yeah, and we do this by decreasing or increasing the phase values as long as we get the difference. One thing, you can't increase or decrease infinitely, of course. In the phase spectrum, it's from -pi to pi, so otherwise it wraps around. So we don't modify values which are too near at the end. Okay. Yeah, an example. So, yeah, you see the modifications done here. Yeah. Okay. I guess we can proceed. Rainer will tell us something about the implementation.
So now that we've covered the embedding part of our framework, so we've been talking about the echo hiding, spread spectrum, and phase coding, 3 different algorithms. I think we should also mention the data rate we can reach using these complex algorithms. Maybe you can give us an example of.
Oh yeah, sorry. Okay, so with echo hiding, I mentioned you can just configure the block size appropriately. Of course, it shouldn't be too low. For example, we took like 20 milliseconds, and you get your data rate. With spread spectrum, you get the robustness due to the spreading. So if you take, for example, 1,000 chips per bit, your data rate is somewhere, I don't know, very, very low, but nobody will corrupt your signal. But we had data rates for about, at about 1.5 to 3 bits per second.
Yeah, this data rate is pretty low, so you can just use it to transmit information, short information like keys for encryption, which is then happening. So now that we have covered the embedding part of our framework, I also want to give you a brief overview of the protocol layer we are using. And the protocol layer is just used to implement something which is similar to the TCP/IP protocol. So the secret data is extended by like sequence numbers or the exchange of acknowledgements, so that we can make sure that the data, the secret data, arrives in the correct order, which is pretty important because if you think of transmitting encrypted data, it's very important for every bit to be correct, because if you have an encrypted block and just a single bit flips, everything is blown up and you can't use it anymore. So this is implemented in the protocol layer, and in the presentation layer here, we just represent the data which is extended by the protocol information as bits and then handed over to the embedding process. Or in case of an extraction, the secret information is put up to the upper layers like presentation and protocol. So to test the embedding algorithms, we also implemented some parts more, and we call them defense parts. And these defense parts let us introduce some noise on the transmission channel, like noise, like real noise, as you may know it. It's just a random signal with a low amplitude, and we add this to the Stega object. We also tried around with jitter, and jitter is a variation of the delay in which we let the packets go over the network. Frequency shifting means to put up the tones, like in semitones, so very low frequencies. And signal canceling means that we just leave out some samples on the way to its destination, meaning we transmit silence. This is not Stega analysis. Stega analysis is like in cryptology, cryptanalysis, finding out if an encryption algorithm is pretty secure. This is just for testing purposes. We just want to try how robust our transmission and embedding algorithms are. Regarding the implementation, we implemented this framework on the Linux Intel platform, meaning 32 and 64-bit environments, but we also ported it to the MIPSL platform, and the MIPSL platform can often be found on smaller or embedded devices, such as customer routers or Soho routers, in the price range of about, let's say, 70 euros. And in this case, we took the Asus WL500G Premium version 1, which isn't available anymore, but it's based on the Broadcom 4704 chip. And we were able to port our framework using a modified OpenWRT SDK. Maybe you've heard of OpenWRT. This is some kind of Linux distribution which can be used on embedded devices, such as these routers. We also think of porting this whole framework to other platforms, and to do so, we need platforms which support or which provide either a routing interface or an audio interface. I also want to tell you something about this modified OpenWRT SDK. And the most important thing is there is no support for NFQ. This is the net filter queue for processing packets in user space, as mentioned before on one of the first slides. But yeah, there's a patch for that. So we added support for NFQ in the OpenWRT SDK. And we also needed to install additional packages. Most notably is the FFTW library for FFT transformation of auditive signals, and for example the GNU Scientific Library, GSL. And to be able to run this whole thing on these embedded platforms, we for sure needed to adapt the firewall settings and the start scripts to fire up our framework. So we also think of porting this framework to smartphones, and I think this is the most interesting feature. If you port this to smartphones, and if you are able to attach to the raw voice data, meaning the sound card of the smartphone, you would be able to communicate with steganography over a GSM network, meaning you have your steganographic tool with you in your pocket all the time. So for smartphones, we thought of the end of Android powered smartphones, and the good thing is in this case there is the NDK, and the NDK provides a C++ compiler which is required to compile our source code. If this scenario with the raw voice data does not work, we can also think of using it for voice over IP, meaning we would need to be able to modify packets which leave a smartphone using this NFQ mentioned before. Now to bring our presentation to an end, we prepared a demonstration setup, and this demonstration setup is, in my opinion, pretty complex. So we have 3 computers, and 2 of them are virtual machines. One is called Alice, the other one is called Bob. And on each of these 3 machines, there is both the framework as well as the GUI running. So you might ask, what's the purpose of the 3rd machine? So the 3rd machine is this laptop itself, so it's the host. And on this host, we configured the framework in defense mode. So we take the RTP packets, which pass from from Bob to Alice, and add some noise so that we can demonstrate the robustness of the transmission of secret data using steganography. What else you need to know? There is 2 dedicated subnets, and to these subnets, the virtual machines are connected. So let's see. Here we have, so as mentioned before, the whole thing consists of 2 parts. It's the framework itself, which is an ordinary process, just running and waiting for connections. And then there is the GUI, the graphical user interface, and here we have the host. So the graphical user interface here is used to add noise to real-time packets, RTP packets, which pass through the host. And we can do this by sliding this bar up or down. And currently it's set to not introducing any noise. So here we have Alice. This is the Alice computer, virtual machine. And on this Alice computer, we have the framework and the GUI, as well as a voice over IP client. And we decided to use Ekiga, which you might know. So, and the 3rd and 2nd computer is here, it's Bob. And here we have the same components as we have them on Alice. So let's fire up the GUI of our project. Here we have a terminal on which we start the framework, this process, and now it's waiting for our GUI to connect to it. So we connect, and to see if it really works, we implemented some comments, so we can request the configuration of the framework, for example. And to start the whole thing, we send it a start command. So now we have set up the first virtual machine, meaning this is Bob. So now we have the framework running, we have the GUI connected to it, there is the voice over IP client waiting for connections because it's Alice calling Bob. And so we just need to do the same thing on Alice computer. So we start the GUI here as well. Here we start the framework. So it's waiting for connections from the GUI. We connect to it, and we just send it the start command immediately. Yeah, it's now waiting for RTP packets to pass through. So to do so, we start Ikiga, the voice over IP phone, and we call Bob through the host computer. So it's the two virtual machines communicating over voice over IP. So, and now before I hook up, we introduced some WAV file, so that you can hear something in which we embed the information. Okay, that's embarrassing. No, actually, no, sorry. Usually it's fast enough, and you can hear that there's no at least with your ears, you shouldn't be able to hear the modification. Okay, so, yeah, just imagine it's working, okay?
Okay, but okay, but
sorry.
Okay, what we see here, these values. So this is what I mentioned with the correlation. So we see if the guy doesn't speak, the values are very good, and if he starts speaking, maybe there's some interferences, whatever. And but the values are still very good. And what is the range? It goes from 1 to -1. So a 1 bit, the best 1 bit received is 1.0. The best 0 bit received is -1.0. And the worst case is 0.0, of course. Yeah, so this way we decide which bit we actually received. So maybe you could show the GUI?
Yes. So here we have the GUI.
And this tab shows all the interesting information from our layered model. So the little TCP/IP. We have the frames, the packets, and at the top the stream. So if we start chatting,
I will enter something like, say, hi. I will only enter hi because, as mentioned before, the bitrate is pretty low. And so it starts sending, it's putting the bits here onto these layers we mentioned before, and I will switch over to the receiver side.
And in some point of time it will start receiving? Yeah. No. So, yeah, what happens is clear, I guess. So the one, I guess it's Bob. No, it's Alice, which embeds the bits, and Bob receives them. And yeah.
So, as mentioned before, we also have the defense, which allows us to put some noise into the packets. So, if I put up the slider, maybe you can hear the noise.
Okay, so now we kind of disturb the channel, and what we see, the values which I mentioned before go down by some factor. Yeah, it's when you turn on the noise to 100%, of course, the values will be very bad. In this case, it's still okay. It's still more than enough to decide what bit we extract.
Okay. I will stop this. Okay. So this is all running, no problem. So here we have the demonstration setup, as mentioned before, 3 computers, all with the framework and GUI. As a last slide, I just wanted to give you an outlook. So we brainstormed a little bit of future scenarios, what we can do, and I think it's important to have a better usability and to provide the community or all people that are interested to be able to communicate securely. And so this could be, for example, a Windows port or ports to smaller and other devices which you're able to put in your pockets. So let's say thank you for your attention, and if you have any questions.
Okay, there's one question from the peace missions. So the one is asking if there's a measure to say how detectable embedded messages are, and is a secret required to find out if there's a hidden message at all?
Okay, so yeah, of course there are techniques from stack analysis. We didn't, as mentioned on the slides, we didn't like try to analyze something, maybe a follow-up project. For now, it's to say that we did our best to not be detectable.
Okay, my question, what was the bits we see in the debug log? We see there is a 1 or 0 bit. So for what standards is when no message is sent? Which bits are there?
Okay, so it depends on the protocol used. In this case, we used the stream, which was shown in the graphical interface. And if there's no data, so no chatting in this case, then it just sends acknowledgements, just for testing.
Okay, then another question from Peace Missions. So the one is asking for a link to the project and if this is available in open source.
We are currently trying to make it open source. Now, it's open source, but we are just working to setting all up, meaning a project page, and we also need to talk to the project partners because it's a funded project, and to find out how we can do it best to make it available for the community.
Yeah, and I had some nostalgic feelings during your presentation, because tomorrow, 16 years ago, the 29th of December 1994, I saw a very similar presentation at the Chaos Communication Congress by, at that time, student Andreas Pfitzmann, and he built a system where you had a video chat and you could chat with your keyboard at the same time and transfer information. And just out of mere interest, did you have access to that project?
Not exactly to this one. There are related projects, for sure. For example, there is this famous paper called Techniques of Data Hiding, and almost all embedding algorithms that we implemented are based on this paper, for example. It's like a reference paper, but it was a requirement for us to implement something new. So we implemented new algorithms which combined these algorithms as presented before. But no, to this project, I didn't know about it, to be honest.
May I add something here? We didn't know about it, yeah. But one thing, most projects out there still use LSB hiding. Also, there are very much papers on the stack analysis, but most focus on LSB hiding. So in our case, we really wanted to focus on other algorithms. I don't know what Mr. Pfitzmann used back then, but chances are that he also used or implemented the whole stuff with LSB hiding.
And the main problem with LSP is that it's not really robust. If you do, for example, a conversion between formats, let's say from WAV to MP3, or the worst case is if you convert the data to the GSM codecs, then there's no chance for LSP algorithms to survive that. And this is absolutely the case here. So we definitely want to, for our data to survive this media conversions.
Okay, the last one is via Twitter. They like your slides and they ask if you're going to publish them.
Yes, we do.
Yeah, okay, sorry.
No.
Yeah, I guess they're still, they're actually in the pentapath. I don't know if it's the latest version, but we'll upload them in 7 minutes. So yeah, they're available.
If I understood that right, the three embedding techniques should not interfere with each other. So is it possible to combine them to yield higher data rates or add robustness?
Yeah, good question. There is the possibility, of course. One problem you may get is the more you embed into the audio signal, so the higher the modifications, or the more, and the easier it is to be detectable, or at least to distort the quality of the audio signal. But yeah, I guess it's possible.
So, I don't see any other questions in the audience. So, I want to thank you for your very interesting talk. Yeah.
Thanks for the audience.
Thank you.